Okay, gang. So welcome to CSC 475. Can you guys hear me? If someone would please type in the chat if they can hear me, that would be great. Awesome. Thanks, Zach. Thanks, Haley. Thanks, Dave. Thanks, everyone. So that's good. Like I said, welcome. An issue, or one issue that we may have is that in the spring, those of you who may have had my CSC 310 class, I did that with OBS, and I didn't do video of myself. I'm self-conscious, like a lot of us are, seeing ourselves on video with my long hair and all that crap. But I decided that it might be a little bit more like real life if you could see me at least occasionally on the video. And also too, those of you who had my CSC 310 in the spring know that I did it with OBS. So they were recorded lectures. I didn't do it live. This time I'm going to attempt to do it live. And one good thing about that is those of you who remember 310 know that on some of my lectures I would go 2.5 hours. I'm sorry. But by doing it live, that'll force me to keep it to 1 hour and 50 minutes. So it'll be a lot more like if I were sitting there in front of you guys. And I'm trying to get a little bit fancy by putting a logo behind me so you don't have to see my messy house. And we'll see how that goes. It should be possible if you've got questions to put them in chat. I'll try to keep the chat window open. Obviously, you know, we can't have. I see there are 34 of you right now, but I think altogether there are closer to 50 people who are signed up between the two sections of CSC 475-01 and 02. So we'll do it Zoom. We'll do it live. You've got the link, obviously, since you're here. The rest of the people, I hope they access Moodle because that's where the link is. Did anybody run into problems accessing Moodle? I had one student send me an email saying that that for some reason the course didn't show up on their Moodle. So is there anyone in the room who is here but doesn't see the notes or anything on Moodle? Because that was weird. We had one student tell me that. I don't see anybody typing in yes, so I assume that means that all of you were able to get the Moodle stuff. Thanks, Michael, for letting me know. Okay. So again, you know, because I'm using Zoom this quarter, and in the spring I was using OBS, I'm not really good at Zoom, so it's going to take me a little while to get fluid on things. But what I'm trying to do is, the plan is that I'm going to record these lectures on Zoom to the cloud, and then I'm going to make them available after the fact. Now, back in the spring, I was actually in Phoenix, Arizona, for those of you who didn't know, and I had a really good internet connection. But now, though you can't see it behind the Louisiana Tech background, I'm sitting in my house here in Ruston, and as all of you who live off campus and have Suddenlink know, Suddenlink is not that good. And so during the day, my internet resets itself. It's usually out for 5 minutes or so. The router resets itself. Yes, I agree, Logan, it is trash. But as I was saying, the internet here is terrible. So how am I going to address that? Well, if I completely lose internet and it goes out for a long time and you lose access to the stream, then keep checking back during the 2 hours. And if it's a total disaster, what I'll do is after the fact, I'll record the lecture, or if we got through half the lecture or something like that through Zoom, I'll summarize the second half of it, and I'll post these. So there will be videos. So even if stuff craps out on us, there will be videos of the lectures. They will be posted to Moodle, or else I'll have a link in Moodle and actually host them on YouTube. I put my OBSs on Moodle in the spring, and that seemed to work fine. Nobody had a problem with it. So I may do the same thing, and no one complained, although I heard that some people, some faculty members were like, oh, you're not supposed to put them on Moodle because you're going to use up too much space. And I'm like, yeah, that's not my problem. Sorry. But anyway, either they'll be on Moodle or there'll be a link from Moodle to the lectures. Now I am trying something here today. Oh, look at that! My background went away for some reason, so you can see my messy house. I don't know why that happened. I didn't do anything. Anyway, as I was saying, I'm trying something different. I've been experimenting the last couple of days, and I'm connecting in through my cell phone for the audio and through my laptop for the video. And the idea is that I think, I've done a couple of experiments and I think this works, that if my internet dies, I believe that you will still be able to hear me and the room won't go offline if my phone is still connected. And of course the phone is over AT&T, which is far more reliable than Suddenlink. It is a very clean ceiling. Thank you. Actually, it's not such a clean ceiling. If you could see all the dust bunnies, you wouldn't say that. But anyway, as I was saying, I am connected by my phone, and I think we're going to find out at some point when the internet dies. I think that the recording will continue and we can stay in the room. What I'm going to do is most days I'm going to post the notes for the lecture ahead of the lecture. And so if my video dies, but I still have a phone connection, and you have the same notes that I'm just going to throw up here on the screen, well then we should be able to plow along okay. And then of course when my internet comes back, I'll reconnect my video. I think that's going to work. I've done a couple of experiments and it seemed to work, but we're not going to really know until it goes out. So anyway, that's what I'm some of the things that I'm trying to do. So let's start out. I'm going to pull up my my syllabus here. The syllabus is online, so you should be able to you should be able to have a copy of the syllabus in addition to sorry. Oh, trying to move it around so that I can actually scroll through it. So again, CSC 475. These are two sections are being taught at the same time here, section 01 and 02. The course material, you don't have to worry about buying a book. There's no book. There are lecture notes, as I said, which I will make available on Moodle. I have here after each lecture. Again, I may start putting them up before the lecture so that you have them in case we lose video, and we can try to still plow through the audio. Some of the course material besides the lecture notes is chapters 14 and 15 from The Science of Computing, an overview by Mike O'Neill. You may have heard of him. That was a book that I wrote for CSC 100. CSC 100 was the precursor class to the 130, 131, 132 series. And in fact, some of the chapters from that book have been melded into the material that you guys covered in the 130 series. So I gave John Gordon, Anki, and them permission to lift liberally from that text. But towards the back of the text, I had two chapters. I had one on artificial intelligence and one on the past, present, and future of computing. And so those two chapters are relevant for this class. The material went way, way, way too in depth for freshmen. But I broke it up. The first chapter 14 that deals with AI, the first section of it's very easy to read. It's just an overview of the history and stuff like that. And then the second half, and really the last 2/3 of the chapter, really went into a lot more depth. And I didn't expect students to read that or work through it, but a lot of students do come to computer science because they're interested in artificial intelligence. So I went kind of, well, screw it, I'm going to put this in here. And so the student who's really interested, they can go ahead and start reading that and get an idea of what AI is about. So that's chapter 14, which we'll pull pieces from. And chapter 15 is, like I said, the past, present, and future of computing. And in that, I talked a little bit about AI and where things are going, and even mentioned the singularity and things like that. And we'll talk about that a little bit here in this class as well. The other text is Neural Networks and Deep Learning by Mike Nelson. It's a free book. There's the link to it. We really only go through the first two chapters of it, but it's a great book if you really want to learn about deep neural networks, if you want to learn about machine learning. And then there's going to be various online material that I'll put up, occasionally articles, things like that I think you might be interested in. And so for those of you guys said that you have access to Moodle, well, I've already put links to these course materials on Moodle already, so it's there for you. Class meetings, again, 2 to 3:50, Tuesday, Thursday on Zoom. We're using my personal Zoom right now. If that works, we'll leave it like that. I could come up with a separate link just for the class, but I don't see a need to right now. So we'll just use my personal room. You guys know I'm Mike O'Neill. A lot of you, I recognize your names. You've already had me for a class or two. Some of you, you guys are new to me. So talk to your friends to find out what you've gotten yourself into. Office hours, they're going to be virtual, 10 to noon weekdays, and also at the Zoom. I'm going to make a real effort to be available from 10 to 12 and logged into Zoom every day, so that if you have questions, they're office hours, just like normal office hours. You can stop by to see me there. If I don't react, you might, ping me, start screaming something to let me know you're in the room, because I actually have two computers here, and I'm going to be working on lecture notes and stuff like that. So so I may not always be on camera, and I may have my camera off and the mic muted and stuff like that. But I'll be in the room from 10 to 12. Again, I know some of you are taking classes in person. I know some of you are taking classes in hybrid. I know some of you are taking classes fully online. Many of you were probably expecting this class to be in person. Again, I don't want to go into the details, but due to I'm about to turn 60 and I've got some health issues, stuff that slows me down, anything like that. But, I'm at much higher risk of a negative outcome with COVID than you guys are. And so I just decided that it would be better for me to offer the class online. There's less chance I'll get sick and you guys would miss my lectures, right? So we can't have that happen. So that's the reason for this. Now, as we will see, it's technically listed as a hybrid class rather than as an online class because the midterm and the final are planned to be in person. If you cannot meet in person because of COVID, you need to let me know. And you have to go through disability services and do an accommodation. I had to do the same thing. And I've already gotten information from 2 of you that you're signed up through there, and we'll work out something as to how we will do those exams for those of you who have accommodation requests. Might be online. Maybe one other idea I had is check with the testing center and see whether or not they are setting up so that they can give exams in isolation. That might be another option. I don't know yet. Like I said, if you're in that category, let me know as soon as possible, and we'll work out something so that you can do the midterm and the final. Okay, so what's the description of this course? Well, one way to start with that is to look at, the catalog, and the course catalog reads, the design and implementation of artificially intelligent programs. Topics include gameplay, heuristic search, logic, knowledge representation, and reasoning strategies. Social implications are discussed. Well, that's a pretty decent summary of AI from about 20 years ago when I wrote it. It's still a pretty good explanation of what AI is. It just misses about a third of the class, maybe closer to half. There's no mention of machine learning there, as you might notice, but we will cover machine learning. So the course catalog description is a little bit dated, but we'll work our way through it. So what are we really going to do? We're really going to do 3 things, okay? The first thing is going to be these first 2 weeks, except for today's lecture. Today's lectures, Mike likes to play lectures, so after we cover all this crap, can you hold on a second, please? Because my dryer, this is what happens when you teach from home. My dryer is buzzing at me, so give me one moment to turn that off. Note to self for the future: make sure you're not drying clothes when you begin a lecture. Okay, so there's 3 components. The first one is about the first 2 weeks of class, an overview of what AI is, the history of AI, the impact that AI has on society, the implications of where AI how it affects things, how it's likely to affect things in the future, and also the potential for AI moving forward. This material is not at all intellectually challenging, okay? But it is intellectually stimulating. So what do I mean by that? I mean, it's fun, it's interesting, it's good to think about all of these things. And honestly, I think it would be a sin to teach an AI course and not talk about this. Yes, the details of the algorithms are extremely important, but you need a framework. to be able to understand what AI is. And, you know, there are a lot of college courses that don't cover it, that leave this out. And because a lot of professors just feel uncomfortable talking about things that are a little bit more amorphous, you know, or big picture or philosophical. But those of you who've sat down and had a drink with me know that I love to talk about those things. And they're important. They're probably more important than the details of alpha beta pruning or backpropagation. Okay. So we'll take 2 weeks and we'll talk about that. Please, please, please do not take from this, oh, this is an easy course, right? I've had 3 lectures in it. We're a week and a half in, and it's just been cool stuff. And Mike showed us some videos, and we talked about all these neat things. Yeah, the first 2 weeks is like that, but then we move on into machine learning, and we're going to get serious. We're going to talk about perceptrons. We're going to talk about multi-layer networks. We're going to talk about deep learning. We're going to talk about it in detail. We're going to talk about the architecture of feed-forward networks. We're going to talk about stochastic gradient descent. We're going to talk about backpropagation. And we're going to talk about these things in detail, in enough detail that you yourselves are going to be able to write from scratch a multi-layer, usually a 3-layer feed-forward network that will be able to recognize handwritten digits. And it's not going to be something where you use a tool and just fiddle with it. You're writing this thing from scratch, okay? You are implementing all of the matrix calculations that need to be done. It's a real program, okay? And you really need to be able to program to be able to do it successfully. So it gets serious really quick there. That's a little more than a third of the class. About 4 weeks of the class is perceptrons, multi-layer networks, deep learning, those sorts of things. And it'll culminate, as I said, in this program. I think I have you guys write it in Java. Please don't croak. You might say, Java, that's not an AI language. Well, I don't want you to write it in an AI language. I want you to write it in a normal object-oriented procedural language to show me that you have learned the algorithms so that you know actually at a very detailed level how a multi-layer feed-forward network works, okay? You can go off and you can learn a tool on your own. But if you don't have the mathematical foundations and a deep understanding of the algorithms under there, you're playing at a surface level. You don't really know what's going on. And for those of you who've had me for classes before, if you had my graphics class, for example, you know that I like students to have a high level knowledge of a lot of stuff, and then I like to slice and go really, really deep in a couple of areas. Because you need a combination. You need the big picture overview. You need to be able to see the forest, but you also need to be able to take a tree and study that tree, its bark, its leaves, everything, its root system, so that you'll really know what a tree is. So you have to know what a forest is, and you also have to know what a tree is. So we'll look at a couple of trees, and we'll look at the forest. And so one of the trees is machine learning, and you will implement a program. If you like to program, you're going to love this class. If you really want to know what AI is, you're going to love this class. If you're looking for an easy elective, you can still drop and take something else, because there are many other courses that we offer here at Tech that are senior level electives that don't require the workload that this course requires. Okay, so it's up to you. This course is a lot more work, but you will learn what the fundamentals of artificial intelligence. And if you have any desire to go to graduate school or anything like that and really start learning about AI, this class will provide an excellent foundation for doing so. So machine learning, that's sort of the second piece of the class, the middle section of the class. But it's not the whole class. And some students, they look at this and they go, but Mike, machine learning is everything now. Why aren't you make the whole class machine learning? And I'm like, well, you know, 10 years ago, 5 years ago even, machine learning was a little backwater that almost no one studied, okay? And now it's like the hottest topic, but it's not new. Perceptrons go back to the late 1950s, okay? When I was a student working on my PhD in the late 1980s, the textbook that I used for that my professor used for that class, that later I used that same textbook when I taught AI in the 1990s, okay, and early 2000s. That textbook, which was one of the standard textbooks used across the nation, across the world, to teach college level, senior level college AI, it had 2 paragraphs about machine learning. In the whole book, 2 paragraphs. And it said, oh, we've tried this and it doesn't work. And that was it, okay? So, and now machine learning has changed the world. So, you don't know where things are going to go, okay? You guys are 20, 22, 23, okay? I'm going to be turning 60 here, okay? But the point of the matter is that you're going to work for 40 or 50 years. What's the world going to be like in 20 years? What's the field of AI going to be like in 20 years? I don't know, right? So we do cover machine learning, and we cover it in detail because it is currently the thing that's changing the world as far as AI is concerned. But we also cover classical AI, sometimes called good old-fashioned AI, right? Machine learning, for those of you who've read a little bit about it, you write a computer program, but the computer program is not a computer program to solve the problem. The computer program builds a computational model, a multi-level network, and then you train that network on examples, okay? So the network learns on its own. And in the end, you don't know what the network has really learned. It's if you could open it up, which you can, it's just a bunch of numerical weights. You know, there are no, from the network's point of view, there are no variables. They're just little simulated neurons with simulated weights that connect them together. And so you can't go in and look at the subroutine for doing so-and-so or find the object, you know, to do whatever. So it's very, very different from, quote, normal computer science. While classical AI is classical AI. It's traditional programming techniques applied to the problem of creating an artificial intelligence. So data structures, algorithms, all of those sorts of things. And so in classical AI, we'll talk about gameplay and search. You will have seen some of that in 325. You know, you should have talked about binary trees and binary tree searches. We'll talk about trees and searches. They won't be binary trees. They could be if there's only 2 choices, but most of the time there are a lot more than 2 choices that you have to make. So, so trees and gameplay. You might say, well, what does gameplay and search and trees have to do with one another? Well, think about a game like a game of checkers. The way classical AI works on that is it says, okay, the human made a move. So here's the configuration of the board. What are the valid moves? And it can compute those. If you know the rules of the game, it can compute the valid moves. And so then the computer plays an elaborate game of what if. It says, okay, what if the user moves here? Okay, what if the user moves here? What if the user moves here? And then from each of those, you can see a tree from the current state beginning to branch out into possibilities. And then each of those possibilities, you model what the human could do, what your opponent could do. And you look at all of those. And then from those states, you look at all of the valid moves from there. And so you build basically a tree of possibilities out. And your algorithm is such that it has what's called a heuristic to judge the value of those states. And so basically, the computer is using brute force tree search to be able to look in the future at this move could lead to this move, could lead to this move. And it does that in a minimax so that it can maximize its chances of winning and minimize your chances of winning. And so that's classical gameplay. Your second programming assignment will be to implement a game, usually Othello, sometimes checkers, usually Othello, and build a computer program, classical computer program, that can beat you at that game. Beat yourself. So you're going to write a program that's going to be able to beat you at the game that you programmed the computer to play. Kind of cool. And you can see why when humans first started being able to do that in the late 1950s, people got all excited because people were writing programs where once the program to play a game that they knew, and the machine was able to play the game better than the human. Well, you know, that's a scary and exciting thought. That's why people thought in the late 1950s and early 1960s that computers were going to take over the world by 1970 or 1980. So you hear people talking about the singularity. You hear people talking about, you know, Elon Musk talking about computers taking over the world. Yeah, it's interesting. Maybe he's right, you know, but people were having those same conversations 60 years ago when I was born. Okay, so think about that. You have to put things into perspective. After game playing, we're going to talk about propositional logic. You already know something about logic and or not from digital logic. So we'll start off there, and then we'll move on from there to talk about logic systems that can reason and using inference. And it's fascinating because what is formal logic? One really true way of explaining what formal logic in a computer does is it's reasoning without understanding. Reasoning without understanding. The system's able to reason, but it really doesn't understand what it's reasoning about. And you might think, well, that's kind of weird. Yeah, but how many of you have heard of GPT-3? Okay, everybody's been talking about that for the last couple of months. It's the new system that can write stories like a human, and actually it can program, believe it or not, and do all sorts of really, really cool stuff. But it still couldn't understand a story in the way a 4 or 5-year-old could. You could go to a 4 or 5-year-old, say your niece or your nephew, and explain something to them, how something works. So read them a story and ask them about it. No computer on the face of this planet can do that. We don't have any computer that can reason in a general sense the way a 4 or 5-year-old human can do. And that's with machine learning. So, pretty interesting. Okay, I've talked a lot about all that. Let's talk about our grading policy. There's going to be, like I said, we've already covered, well, I covered 2 of these 3 things. There's going to be 3 assignments worth 40% of your course grade. The first one's going to be a research paper. And remember, we've got these 3 components to the class, right? We've got the overview, the machine learning, and the classical AI. Well, I can't give you a programming assignment on the overview. So instead, I'm going to give you a research paper on that. I think the syllabus says that it's officially assigned today. Clearly, I'm not doing that today, but I will try to work up the description of the research paper probably tomorrow. Get it online either tomorrow, Friday, or Monday, and you'll have about 2 weeks to write the paper. It's just going to be on some aspect of AI that you're interested in. It's going to be worth 10% of your grade, so a letter grade. So it's important, but it'll be on some whatever aspect of AI you're interested in. Excuse me. We've already talked about the neural network assignment. That's 15%. And we've already talked about the Othello programming assignment. That's another 15%. You've got to score at least 50% on the individual assignments, including the research paper and the programs, in order to pass the class. 50%, you've got to make at least a 50% on each of these 3 things: the research paper, the machine learning programming assignment, and the classical AI assignment. Why? Well, about 3 or 4 years ago, I had a student come up to me who was taking a class, and I asked him about his research paper. He said, "Yeah, I'm not going to do that. It's only worth 10%. I was like, okay. And he was like, "Well, I'm already going to make a B anyway." And I was thinking, I guess that you can do that, but no student's ever going to do that again because I'm going to make it so that you can't do that. Why? Because Mike is mean? No. Because I'm trying to, we're here, this is an elective. We're here to learn about AI, okay? And there are different aspects of it. And I think writing a paper on some aspect of AI, going deep into the woods on some particular area that you find interesting, is an important thing. So you'll come out of the class really, really knowing about some general topic in artificial intelligence. So that's why you've got to get at least half on the research paper. Same thing with the neural network. If you come out of this class and you have no idea how to program a neural network, then you haven't really accomplished the class purpose. And same thing with a game playing program. If you can't write a game playing program, that can beat you, then why did we go through this exercise? You didn't really learn the material. So anyway, like I've already said, bottom line, if you don't know how to write complex programs or enjoy coding, and some people don't enjoy coding and they're in computer science, and or you can't stomach writing a research paper, please just take a different elective. No one has to take this course, okay? I seem like I'm trying to get you to drop the class. I don't mean that. What I mean is, if you want to learn about AI, you're going to love this class, okay? But if you're looking for an easy class to keep your GPA up because you got 3,000 other things to do, take a pass on it. Do something else, because I'm going to work your butt off in this class. But hopefully it's doing stuff that you enjoy doing and learning a lot. So that's the plan. Group project, there's no group project in this class. And the reason why there's no group project in this class is I used to have a group project, and then I had some of my very best students come to me basically and say, "Mike, I love your class, but you're killing me." the workload is insane. So I've dropped the group project. It was getting a bit ridiculous. So I'd love to have a group project, but no, if you're interested in group project or some kind of a deep project, in AI, and you're really interested, you can always talk to me about maybe doing a 490 project or something like that under my direction. I always have, ideas and things. There's going to be 2 exams. They're worth 60% of the course. Exam 1 is 30. Exam 2 is 30. Exam 2 is comprehensive. My final is always comprehensive. While the lectures are online, I do plan for the exams to be in person, as I said. Technically, section 1 is going to be in integrated engineering and science building in 216, and section 2 in 218. I believe the way it's going to be set up is the divider between those rooms will be open, and there's just going to be one giant room. I've been assured by Galen Turner that the room is big enough, given the number of students who are taking this class, that you will be able to social distance properly there. And again, like I said earlier, if you've got a COVID-related problem, get in touch with me, and we'll see if we can work out something. Curve, students always ask, Mike, do you curve? If you've had a class of mine, you know, usually in the end I apply a small curve. I never curve grades downwards. So, if you get a 79.6, right, that's a B. I never make that a C. So you'll always get the grade that you earned, but sometimes maybe you made a 78.8 or a 79.1. Those might be a B. So the way I do things is, here's a pet peeve. I hate professors who say it is, a 10-point curve, and if you're, 1/10 of a point below something, well, then that's just it. That's the way the grades are. Sounds good. A lot of engineers approach things that way because they like things very cut and dry. But the reality is that I cannot tell you the difference between a 79.7 and a 79.4. I am not a perfect grader, okay? Though I try really, really hard to be a consistent grader. Put a lot of effort into it. I do things like I hide your names from myself so I don't know whose exam I'm grading, because maybe I know you and I like you and we've had some good conversations. I don't want that to cause me to give you a higher grade than you earned. Or, maybe for some reason you and I have had a run-in and we didn't hit it off or something like that. That shouldn't affect your grade either. So the best way is for me to grade where I don't see your name. And so I tend to grade a page at a time. Yeah, your name's on the front page, but when I get to page 2, 3, 4, and 5, I have no idea who I'm grading. And I like it that way because I don't want personality to affect the objectivity of my grading. That said, it's still impossible if I'm grading 50 papers, okay, even though I take notes when I give partial credit, right, I can't grade all 50 of those at the same time. So I might grade them over 2 or 3 days. Trying to remember, I took off, 2 points here for this person, and here's a similar answer, maybe I take off 3 points, or maybe I take off 1 point. Again, I try very hard to be completely consistent, and I do take notes on what I took off points for, but you tell me. I mean, if you can grade perfectly, fantastic, because I'm a human being and I can't. So what I do with grades is I try to look for groupings, and it varies from quarter to quarter, but usually there will be a pretty big gap between the B's and the C's, like maybe 2 or 3 points, right, when it comes to the average. And sometimes you know, maybe your lowest B is an 82 and your highest C is a 78. Well, then you go, okay, I feel real comfortable giving these people B's and giving these people C's. But maybe your B group, you know, is like 82, 81, 80, 79, and then the next group starts at about 76. Well, those 79s ought to be up in the B group because they clustered together. So that's basically what I do. I kind of eyeball cluster the grades. Hopefully it doesn't become a cluster F. but I try to eyeball them so that there's never a case where, you know, 0.2 of a point separating an A and a B. Because I can't grade that accurately in that case. So anyway, that's kind of what I do in grading. Important dates. These are in the syllabus as well, but you can see I already pretty much know when we're going to do our exams and when we're going to have our research paper and our programming assignments due. Late assignments, please don't turn anything late. It just pisses me off. And so to keep you from doing that, there's a 50% penalty if an assignment is submitted late within 24 hours past the due date, and then 100% afterwards. I just don't want to see it afterwards. And you know, it just becomes really problematic if people are turning in stuff way after the due date and stuff like that. So I don't want to deal with it. Just, you know, have your assignments turned in by the due dates. I mean, if I write a grant proposal and the National Science Foundation says it's due at 5 p.m. on this date, I can guarantee you that if I turn it in at 5:01 on that date, the National Science Foundation will not look at my proposal. They absolutely will not accept it late by even 1 minute. So deadlines are just something that we have to learn to be able to deal with. Missed exam policy. If you're going to miss an exam, text me or email me beforehand, okay? You're going to get a lot more cooperation from me, and I'm going to be much more willing to work with you if you let me know ahead of time. After the fact, letting me know, oh, I was sick, or oh, this happened, or I'm going to be far less willing to listen to your excuse. Now, things do happen. If you're in an automobile accident on the way to class, dial 911 rather than Mike O'Neill. Okay. In severe cases, we can work things out, but in general, you know, please let me know in advance. The classroom conduct policy, normally there's a whole bunch of crap here about, you know, paying attention and not disturbing the class and stuff like this. Since this is all over Zoom, I just basically said, keep your mic muted unless you're asking a question. So that's our classroom conduct policy, is keep your mic muted when you're in a live lecture over Zoom. Accommodation with disabilities, you got to register with Disability Services and let me know as soon as possible. Academic Honor Code. Yes, I have been asked by administration to include the silliness. More like I have been told by administrators to include the silliness. By enrolling in this class, students pledge the following. Being a student of higher standards, I pledge to embody the principles of academic integrity. Yes, don't cheat. That's really bad. And if I catch you doing that, I will flunk you, and I mean it. But having students recite a ridiculous pledge is ridiculous, because if you already are a person of high integrity and ascribe to the principles of academic integrity, you don't need to take the pledge. And if you don't ascribe to the principles of academic integrity, having you take the pledge does nothing. So to me, that is the height of silliness. COVID-19 related information, we've been asked to include this, and this stuff is important. You can read through it, but I've got links in here to where you can access coronavirus information, basically La Tech coronavirus. There's a return to campus plan. There is a safety and protocol. If you are exposed, if you believe you're exposed, if you develop symptoms, there is a procedure for contacting university officials where they'll do contact tracing and isolation. I also know that there is currently, there was an email about it this morning, please look, about testing on campus. It's going to be done over near the Argent Pavilion in the football stadium. I believe it's free. It didn't say anything about cost there. We need to get a good handle on this. So take it seriously. Some schools have done okay in coming back, in having students come back, and some universities have done terrible at it. And, you know, even though this class is not in person, I was a student once, and I truly understand how important it is for the social aspects of college, of university. And you want to see your friends. And many of you weren't able to be here in the spring. You haven't been here weren't here in the summer. So it's been 6 months since you've seen all your friends. And that's miserable. And I'm sorry the world is that way right now. But you got to remember that your age group, you know, there are bad outcomes. As some of you know, we actually lost a student of tech who passed away from COVID-19. So it's not that you can't have a bad outcome. You can. Your likelihood of having one is far smaller than the likelihood of one of your instructors having a bad outcome, especially older instructors. So, you know, you have to think about, you know, the faculty and staff. And if there's a large outbreak, you know, tech could be forced to go back to fully online, and I don't think any of us want that. So be serious about it. If you do think that you've been exposed or you have symptoms, go through the university policy for that. On the flip side, if you wake up in the morning and you go, oh, I kind of don't want to take that exam that Mike has for me today, you can't just skip it. You have to go through the university COVID reporting system there for your safety, for your health, and for everyone else's health. So, so please take it seriously. I would appreciate that. We've already talked a little bit about potential technical issues during our online lectures. Even if everything dies during the lecture, I'll attempt to carry it on with just my phone. But if that doesn't work out, you can be assured that I will post a video of the lecture. So it's not like it'll be a hassle if we show up and, you know, and we lose connection, but it won't be the end of the world because there will be a video available. In person, potential COVID-19 issues for the exams. Again, it's the wrong place, isn't it? Your instructor's internet connection is prone to dropouts. Yeah, I think that put that in the wrong place, didn't I? I wrote this very late last night. But basically, during exams, follow the standard university procedures for face-to-face instruction, including wearing masks. I don't know what happened there. That's in the wrong section. I think this is the introduction that belongs in the other section. So I think. Anyway, I'll worry about that later. Okay, emergency notification system, sign up for it. Collaboration policy, don't cheat. If you cheat, you're likely to get in a lot of trouble. Don't plagiarize. Don't buy a paper off the internet. I will use Turnitin to do plagiarism checking. So don't do that. Don't go online and pay some Ukrainian to write your paper for you. It's embarrassing. It's embarrassing when you do that. And by the way, I don't mean anything negative about Ukrainians. Excuse me. But there are some people out there, mainly Eastern Europeans, who do speak English, and quite frankly, are in terrible straits economically. And so we all know it's out there. But I can tell when a paper is being written by a Native American. I don't mean a Native American, I mean an American. Especially if I see that, you know, you're from Gonzales and have lived your whole life in Louisiana. You know, it's very easy when I'm reading a paper to tell whether or not it was written by a person who learned English in the South. So don't embarrass yourself by paying someone to do that, because I will know, and it's just embarrassing. So don't do it, please. Exams, basically, I just want your brain, something to write with. That'll be about it. I will have proctors. I'm not going to show up in person for the exam. There'll be a proctor that'll give the exam. But I will grade them. I might have them digitized. I haven't quite decided whether I'm going to have my proctor take the exams, digitize and send me the files electronically, or whether I'm going to actually physically grade all your grubby little papers that your hands have been on. And yes, I'm somewhat of a germaphobe. I apologize. Here's the day-by-day lecture, just so you can see that I put a lot of thought into it. One thing is not listed here on this, and that is Prolog. Prolog is a programming language based on logic, and in the past, I have included Prolog, but when I started going through the schedule again, I tend to load things up, so I dropped it out. That does not mean that that we won't have that we won't cover Prolog. We may. If I find that I'm getting a little bit ahead, I may be able to work in a lecture or two on Prolog at the end. I'm not going to promise it, but if it happens, that would be fantastic. And if it doesn't happen, it doesn't happen. So let me see, now that I'm not screen sharing, I can see the chat again. Let's see, questions. Oh, let's see. Will the final exam date be earlier for graduating seniors? If you are a graduating senior, let me know. And I'll work with you. I usually like to have the exam. I don't really like the exam being the last day of class, but as I worked through the schedule, it just looked like it was going to fall that way. Last time I taught this class, it was a Monday, Wednesday, Friday, and when you move to Tuesday, Thursday, things change around a little bit. So as I was going through the syllabus, it just looked like it all be on the last day. What I frequently do is, if you're a good student, and mainly good students take this class, if you are a good student, you know, and have an A average, and you've got a strong A in the class, or strong, let's say you've got a strong B in the class, a lot of times what I'll do is I'll just estimate. I'll say, well, you know, you got an 87 in the class right now. You did pretty good on your programming assignments. I'm going to guess that you'll have a B, and I'll turn in that B grade for you. You still take the final, and if you end up that you made so good on the final that it moved you to an A, then I'll do a grade change form, so you'll get your A. Excuse me, one second. And you get to see my cool photo from the Bahamas. I need a beer in my hand. I didn't have a beer in my hand, or really, I guess I needed a the rum. Captain Morgan. They didn't have a Captain Morgan, but anyway, that's me in the Bahamas. Oh, let's see. Sorry about that. So yeah. I'll do something like that. Sometimes, though, I have actually given the exam early, but we'll work out something. But I need to know pretty quick if you're a graduating senior, so we can begin planning that. Let's see, here's one. I think you need at least 50% on all assignments. So maybe it's not a net 50%. It's a 50% on each assignment. So you have to make at least a 50% on the term paper, at least a 50% on the machine learning programming assignment, and at least a 50% on the Othello program. Why? I want you to put effort into each of those things. I'm not saying you have to have 100. I'm not saying even you need a 75. I'm saying you need a 50, right? And it's pretty easy to get a 50. You know, if you did some work. I'm not trying to kill anybody. What I'm trying to do is I'm trying to make sure that you really work on all of those on all of the assignments. Let's say someone's an AI program and they can grade perfectly, but they're pretending to be Cody, and that's pretty interesting. So I'm more impressed, not that the AI program can grade perfectly. I'm impressed that the AI program can follow the conversation and join in, because that would be a program that would have passed the Turing test, and that would have won the author, who I assume is Cody, probably a Nobel Prize. So, will I have a clear grading rubric to ensure there will be a grading rubric that will be provided for the programming assignments, so that you'll have a pretty good idea of what you need to do. Now, don't shoot for a 50, shoot for 100, but at the same time, at the same time, I'm trying to do something so that you won't be totally have no idea what grade you. Going in, you should have a pretty good idea of what the grade will be. What is this? Are we meeting next tomorrow as well? Did I say Friday or something? What did I say there? I've got a class Monday, Wednesday, Friday at the same time.
You have been saying Friday a couple times.
Oh, is that in the syllabus, or
it's also in the syllabus?
Yeah, you could, if one of you guys could highlight where I said Monday, Wednesday, Friday, I'll go back and I'll change that. Again, last year when I taught the class, it was Monday, Wednesday, Friday. So when I went through that syllabus, the last page, I had to change all the Monday, Wednesday, Fridays to Tuesday, Thursday, so I could have missed some there. I think the numerical dates should be correct. But if you find some problems in there, highlight it in red, send me a copy, and I'll create an update on that. But no, there are no Friday classes. Now, one thing I did not talk about that we should is how are you going to turn in your programming assignments? You might think, well, I'll just submit them on Moodle or whatever. I have taught for a very long time, and I have struggled with the fact that in many computer science classes, the most difficult things that you do are the programming assignments that you write. But in some classes, they're worth very little. Well, in this class, the paper and the programming assignments are worth 40%. It's getting close to half, really, including the paper. And the programming assignments themselves are each worth, a grade, a letter grade and a half, 15%. Two of them together, that's 3 letter grades, right? Because it's 30 points. So, 70 to 100. How can I be sure that students are writing their own programs? The way that I have decided to handle that, it's a very time-intensive thing on my part. But the deal is that I have meetings with students. Some of those Fridays or Mondays that you see in the schedule are real. If they're in bold and they talk about something being due, student meetings, those are for real. What happens is each student, each of you, when you turn in a programming assignment, you will be required to meet with me. Usually it's in person, but this quarter it's going to be on Zoom. And talk to me about your programming assignment. Show me your code. I'll do a screen share. You'll show me your code. We'll go through it, and I'll say, well, why did you do it like that? Or what does this section of code do? Or, hey, can you scroll down and show me where you did thus and such? And if you can do those things and talk about the code, then I know you wrote it. If you didn't write it, there's not going to be any way in hell that you'll get through a 15-minute conversation with me about your program. Because here's a news flash. If you wrote a program, you're going to be proud of that program, and you're going to want to show me all of the stuff that program can do, right? If you didn't write it, you're going to be so ready to get out of that conversation as quick as possible and tell me as little as possible about the program as you can. It's obvious. And if you can't pass the verbal part of the interview, you don't get credit for the programming assignment. Someone loves ranting about their code to people, even if it's, that's pretty funny. I'm sure your code doesn't suck. But anyway, so we will have meetings, and I can't do all those meetings on one day. So like your programming assignment might be due Monday, and then on say Monday and Tuesday, I'll do I'll do meetings by Zoom back to back. And again, there are 40 people here in the room now. Takes a long time when you're doing 4 an hour. That's 10 hours worth of work straight without even a bathroom break, right? There. So so it's rough on me to do it, but I think it's very important. And that way I know you actually did the programming assignment yourself. It gives you a real incentive to write your own code. And look at it like this. You guys are seniors in computer science, right? Might be a junior, but you're seniors in computer science. If you can't write a program, a relatively complex program, you need to take some sort of self-assessment because that's really bad if you somehow made it to senior status in computer science through 325 and you can't write a program. You should be able to do that. Okay, are there any other questions? Did I miss anybody's question at this point? If I did, can you repost it? because I think I scrolled through all the questions. But the lecture's not over. This is the question break in the middle of it. Are we restricted to Java for the class? Jonathan, I think I require Java on the machine learning one, and I believe I allow more flexibility on the last one. I believe I allow more flexibility on the last programming assignment. But I'm pretty sure it's required to be Java for the first one. Here's another thing. We all have our favorite languages, right? When I was your age, maybe a little older, Lisp was my favorite programming language. And if you want your head to hurt, go and Wikipedia Lisp and look and see what it looks like. It's pretty funny. But you need to be able to program in pretty much any programming language. Here's a story. I love telling stories, as you guys know. I told you that when I took AI, there was no machine learning at all. When I taught AI in the 90s and the early 2000s, I always included a lecture on perceptrons, which was a very early model of machine learning, because I thought they were cool, and I thought that there was some chance that machine learning would at some point in time become important in computing. Isn't Mike brilliant? When no one was talking about it, he was including at least one lecture on perceptrons, which were an early model for machine learning. As I toot my own horn here, I'm glad I did, because it turned out that now they're all the rage. But for multi-level networks with backpropagation, stochastic gradient descent, I never had any of that material. I had to learn it myself. And so after Veer Foha was a professor here at Tech, and he taught the AI class. Well, I taught it, and then I went away and did a startup. And by the time I came back, Veer was teaching it. So there was a break of about almost a decade that I didn't teach the AI class, even though it was one of my loves. But about 4 years ago, I got the opportunity to teach it again, and so I had to teach myself all of the machine learning. Here's another secret. I don't program, okay? Doesn't mean I can't. It means that there are a lot of other things in my life that fill up my time now. I design software. I'm pretty good at that. I've led 2 startup companies where I was the chief architect of the system, but I don't program very often. So when I was relearning or learning for the first time neural networks, I had to I asked myself, I said, Mike, are you going to really assign a program to students that you yourself haven't written? And I went, no, I'm not going to do that. I'm going to write it myself. And so I sat down and said, well, we're going to Java. I said, it'll be Java, because that's a standard language these days. Okay, let me start writing the program. Google, hello world Java. Okay, no, that's the structure. Okay, then I need an if statement. If SourceForge was wonderful, right? So that's what I did. I just Googled the syntax of everything, file IO, and it wasn't bad. I mean, I'm an old man who hadn't programmed in forever, and I was able to write that program in 3 or 4 days, right? With no knowledge. I mean, I knew what Java was. I probably had taught it, long ago, but I hadn't written a program in it in forever. And so my point is that, okay, maybe you love C++, but if you need to be able to write a program in pretty much any language that your prof asks you to. And it's so easy for you guys these days because any example you need of how a particular, what does for loop look like? What is, how do you define an object? Blah, blah. It's all there. You just Google and you got 50,000 examples. And so I don't, some students get really, we haven't used it. Do it yourself. If I can do it, you can do it, right? Because I is old man. If old man can program, student can program. Okay. Sorry, but you should be able to do it. Okay. Other questions? Because I'm about to jump into the second phase here. Cute. Okay. So we've got about 30, 35 minutes left. And what I want to do is I want to talk about some questions to think about. Okay. And the first thing that I want us to look at is something called the Drake equation. How many of you, well, I can't ask how many of you, but yeah, me. How many of you have heard of the Drake equation? Go ahead, tell me, let the chat light up. Or maybe it doesn't. How many of you have heard about the Drake equation? So far, only one brave student. That's the alien thing, right? Yeah, it's something to do with aliens. That's true. Okay, so a few of you, but not a lot. Okay, so let's look at the Drake equation. If I can share my screen on this thing. So what's the Drake equation? The Drake equation is an equation that attempts to estimate the number of technologically advanced alien civilizations in the Milky Way galaxy. And it looks like this. N equals R star times F of P times N of E times F of L times F of I times F of C times capital L. What the is all of that crap? Well, what it is, by the way, when I'm screen sharing, I can't see your chats. So that's why I'm not responding to messages when I'm in screen share mode. I just get a little thing that flashes that shows that there are more of them. So basically, R star is the rate of star formation in the galaxy, but really people kind of just say how many stars are there in the galaxy rather than worrying about the rate at which they form over time. So there are about 100 billion stars in the Milky Way galaxy. So 100 billion stars in the Milky Way galaxy. Now, interestingly, there are about 100 billion galaxies. So, it's a 100 billion times 100 billion would give you the number of stars in the entire universe. But we'll talk about the one little island of stars that we live in, which is the Milky Way galaxy. There's about 100 billion stars there. And then the next term, around those stars, what percentage of them have planets? Okay, because what we're trying to do is figure out how many intelligent alien civilizations that are technological are out there. And so the idea is, well, they got to live on a planet. So how many of our stars have planets? So there's about 100 billion stars. And what fraction of them have planets? Well, we used to not know this, but in the last 5 or so years, there was a mission called Kepler that NASA launched. And Kepler looked at a really teeny tiny slice of the sky and was able to detect a bunch of planets. And then you look at that and you go and there are some statistics you can apply because you can only detect certain kinds of planets and so and systems that are in certain orientations. So by looking at how many you got and saying, well, if all of the other orientations are the same, there should be this many in this section of sky, and this section of sky is what percentage of the total, right? And so applying that kind of math, they came out to be, well, pretty much every star pretty much seems to have at least one planet. So stars without planets are kind of the oddball, not stars with planets. So the fraction of stars that have planets we now know is about 1. So if there are 100 million stars in the Milky Way galaxy, and every star has at least one planet, or most every star has at least one planet, then we can say, well, there should be at least 100 million planets in the Milky Way. That's what that FP is. What about NE? Well, NE is for stars that have planets. What are the average number of planets that can potentially support life? Well, that's a real hard one. We don't really know. Astronomers have come up with something called the Goldilocks zone. It's when you're not too close to the star that you'll burn up and not too far away that you'll freeze. We look for planets in that range. We look for planets about the mass of Earth because we're trying to figure out how many Earth-like planets are there. The best estimate right now, based on Kepler data, is about 40%. Okay, which is pretty good data. So the first 3 terms of that N should give you about 40 billion planets in our Milky Way that are Earth-like to some degree. Now, it may be as bad as Venus or as bad as Mars. So there's a range in there, right? I'm not saying there are 40 billion beautiful Earths out there, but 40 billion reasonable targets that are somewhat Earth-like. So those first 3 terms give you 40 billion. And then from there, it gets a lot more speculative, things that we don't know yet. Like F of L is what fraction of those planets actually develop life? Well, we don't know. And then F of little I is the fraction of those planets that life arose on where there's intelligent civilized life. Okay, because you can have planets that don't have life. You can have planets that got life, but it's all, slime in the sea. It didn't go anywhere. And you can have some maybe that have intelligent civilized life. And then you can ask what fraction of those planets with intelligent life on them have developed technological civilizations that can, have radio and television, can communicate over vast distances, like with radio telescopes. And then you got to multiply all that by how long the civilizations last, because 100 years ago, Earth didn't have the ability to communicate. We didn't have communication technology. Well, 1920, 130 years ago, we didn't have the ability to communicate. But now we do. How long will we last? I don't know. Maybe we'll last millions of years, or maybe we'll blow ourselves up with nuclear war, or maybe the next pandemic, will be more deadly. We just don't know how long civilizations last. It may be a few centuries. It may be millennia. We just don't know. But if you multiply all those things together, you get an estimate of how many civilizations, technological civilizations, there should be in the world. And so the current estimate, like I said, it's 40 billion for the first 3 terms. those last three terms are basically guesses, but most people believe that there are millions of potential civilizations out there that we should be able to communicate with. At least that seems to be what's happening. And the interesting thing is, over the last few years, as we've been able to work our way through these first three terms, when Drake, this equation, by the way, came from a man by the name of Frank Drake. He created it in 1961. Dr. Drake is still alive. He's the head of the SETI project, or he's retired now. He formed the SETI project. When he first came up with this, all of these terms were pretty much totally unknown. But now, like I said, thanks to Kepler and other modern science, we pretty much know the first three terms. We don't know the last four terms, but we've made a lot of progress. So these last four things are guesses, but people think, I mean, if the first three give you 40 billion, that's a lot to work with. These can be tiny fractions, and you still end up with, like I said, hundreds of thousands or millions of civilizations that are out there. So that leads to something. I'm going to stop sharing my screen so I can see the chat, but I'll keep working off of these notes. But that was the Drake equation. Let me see. Yeah, there's some chat in there about but it does take time for radio signals to propagate. So that's the Drake equation, and so by the Drake equation, there should be millions of civilizations that are out there that can communicate with us. How many civilizations have we contacted? How many? So despite all the sci-fi movies, zippo, unless you count us talking to each other, what we're doing here. I'm communicating with you, but non-humans, other planets, zero. And here's another thing too. The Drake equation talks about planets. We now think that there are a lot of moons that may have developed life. Enceladus and Europa, those are moons of Jupiter and Saturn. They're ice. They have ice on the surface of them, but they have oceans underneath because of the tidal forces caused heating. So even though they're way far away from the sun and they're around these gas giant planets, they seem like life might be able to develop there. So it's more than just planets. It can be moons too. So, where is everybody? And that is often called something called the Fermi paradox. The Fermi paradox. The Fermi paradox basically was named after a physicist named Enrico Fermi. And it's funny, this thing came about, basically the scientists were sitting around having lunch one day, and they were talking about UFOs were a big thing there, and they were kidding around with each other, and they were like, well, where is everybody, right? If this was before the Drake equation was formalized, this is back in the 1940s, but people already thought, well, it's likely. I mean, look at all the stars. It's very unlikely that we're alone here. So the Fermi paradox basically says the world, the universe should be teeming with life, but yet we found no one. No one's come to visit us, and we don't have any signs of extraterrestrial intelligence. So what gives? That's basically what Fermi posed. And ever since then, a lot of people have tried to answer the Fermi paradox. In recent years, there's been a concept that's come along by a guy by the name of Robin Hanson. He's actually an economist, okay, a British economist, but he's most famous these days for the concept of the Great Filter. What's the Great Filter? Well, the Great Filter basically says, okay, the Drake equation says there should be millions of civilizations out there that are technological. And by the way, some should be far more technologically advanced than we are, because the sun is a middle-aged star. There were a lot of stars that were born a lot earlier than us, so their planets, the life on them should have been around a lot longer. So everything else being equal, there should be civilizations that are millions of years more advanced than ours. I don't see them. So Hansen says, well, perhaps there are filters, okay, that make things really hard. So maybe one filter is life arising in the first place. Maybe that's very, 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 very hard for life to spontaneously arise, okay? Now, maybe that's true, but if you look at the Earth, if you think of the history of the Earth, this is backwards, so I have to move my hand this way. Think of the history of the Earth as a 24-hour day. Think of it as a 24-hour day. 24-hour day, starting at midnight and going through noon to midnight the next day. So 24 hours. On that clock, I want you to type in chat, guess when life arose. How long had the planet been, how many hours in our 24-hour day had the planet existed before life arose? Go ahead, throw out some guesses there in chat. 10 o'clock, 18, so, you know, in the afternoon, 23, so almost, you know, the whole day. So, in other words, most of you are saying it was like a really long, long time for life to arise on the Earth. Here's the reality. In that 24-hour day, life arose at 3 a.m. Wow. So in other words, life arose almost immediately. If you think about the whole history of the Earth, from the time it was formed to today, life arose. In fact, if you think about that as a day, it arose at about 3 a.m. Okay, good. When did intelligent life arise? So life arose about 3 in the morning. When did we get intelligent life? Or sorry, not intelligent life, sorry, not. Multicellular life, multicellular life. So the first life was just single cells. Multicellular life. 6 a.m., 7 a.m., noon. Somewhere between 6 p.m. and 9 p.m. So in other words, from 3 a.m., so in other words, if life rose in 3 hours, to multicellular life took about 18 hours. 12, 13, 14, 15 hours, okay? So from 3 a.m. to say 6 p.m. So most of the time there was life on Earth, but it was just single cell organisms, algae in the sea, and that was it, okay? So maybe the great filter is multicellular life, right? And if there's a little bit more evidence to believe that maybe that's the case, because if life arose almost immediately after the Earth was formed, right, then maybe it was just the luck of the draw and we were really, really lucky. But all things being equal, you would say, well, it's probably pretty easy for life to arise if it arose so early. But then it took a long, long time to get multicellular life. So maybe multicellular life is really hard. So those are two examples of filters. Maybe it's hard for life to arise, but probably not. Maybe it's hard for multicellular life to arise. There's a little more evidence for that because it took a long, long time. Maybe from multicellular life to tool using intelligent life is the filter, right? So there could be all these different filters here. But the reality is right now we look out and we don't see anybody. Okay, we don't see anybody because there's probably a filter that's keeping these 40 billion worlds from developing intelligent civilizations. Maybe Hansen asks, well, he asks, is the great filter behind us or in front of us? If it's life arising or multicellular life or intelligent life, we've passed through all those stages. So maybe we're past the great filter, the filter that keeps intelligent civilizations from happening. Or maybe the filter's in front of us. Maybe in the Drake equation, that L as to how long intelligent civilizations last is very, very short. Maybe it's 100 years, maybe it's 1,000 years, right? Because something happens to them. They go, and then they're gone, you know. So maybe we're going to go and then be gone. Now, what makes this interesting is that if you're an intellectual kind of person, especially if you're interested in space and things like that, you look at like the probe that we just sent off about a month ago to Mars. It's going to get there next year. Another rover, but this rover is actually designed to look for life. Okay. What happens if that rover finds signs of life on Mars that's different from life on Earth, either current or existed in the past? Well, everybody's going to celebrate. Yay, we found life on Mars. Maybe we don't find life on Mars, but maybe we find life in the oceans of Enceladus here in another 20 or 30 years. If that happens, everybody's going to go, yay, we found life. We're not alone in the universe. And especially if it's multicellular life, species swimming around in the oceans of Enceladus, right, or Europa. Everybody's going to go, yay. But Hansen says you shouldn't go, yay. You should go, oh my God. Because if we find that life exists on another moon or planet in our own little bitty solar system, right? If the first, second, or third time we look for life somewhere else, we find it, especially if it's a multicellular life, we better go, oh! That means that the great filter probably isn't behind us. That life arising or multicellular life arising, those things aren't that great filter that keep intelligent civilizations from being out there. If we find life on Mars or on Enceladus, especially multicellular life, it's an oh shit moment because it increases dramatically the possibility that the filter is ahead of us, right? We haven't lived through the great filter. It's in front of us. That is the contribution, if you want to call it that, of Robin Hansen. Now, what does this have to do with the class that we're currently taking? Well, any of you who ever followed Elon Musk or just about any famous engineer or scientist, Stephen Hawking, I mean, you name it. Many of them have worried about the rise of artificial intelligence. That maybe what happens is humans end up building intelligent systems, and those intelligent systems promptly wipe us out. Anybody who's seen any science fiction is familiar with this sort of an argument. So maybe artificial intelligence is that great filter that we're just about to create. Now you might say, well, Mike, look, if we build an artificial intelligence, you know, it's just a program, it's just software running in the computer. You can turn it off, right? Yeah, well, turn off the internet. Why don't you turn off the internet? Even if we know the internet is dangerous, right? People can crack your passwords, they can destroy your credit rating, they can ruin your social profile, they can dox you. There's all sorts of dangers for individuals being on the internet. There's dangers for countries. All of our infrastructure runs over the internet. And so some of you are in the cybersecurity concentration, so you know all about this. For the United States and other governments plant bombs, software bombs, you know, in the infrastructure of other countries so that we can go in and with a few clicks, you know, we can take down their power grid. People, those of you who were who lived through the hurricane, right? Even some of us up here, I was without power for 36 hours. My sister was without power for almost a week, you know, and it's really, 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 really hard to live in Louisiana without power for an air conditioning for a day and a half, right? If some of the software systems can be set up so that they can cause systems to physically destruct themselves, right? Blow transformers and stuff like that, that can take months and months to repair. So we're talking about, there are real dangers to the internet. There are real dangers to the internet. Are you going to go offline? Is the United States going to go offline? No, because we're completely dependent on it right now. So let's say some AI gets out in the internet. We know it's there and it's doing something, but we don't really know what it's doing. Are we going to really take down the entire internet and destroy ourselves? No, we're not going to do it. We can't. So the idea that, oh, you can just turn it off, that defies logic these days. We're too dependent on computing systems and communication systems to take them down, even if we knew that there was some kind of AI danger in them, because we already know they're filled with danger already, and we use them all the time. So the turn them off, turn the AI off, it's not going to work. Some people say, well, you don't really have anything to worry about because if we don't make it smarter, it won't be smarter, right? Well, you look at something, there's something called Moore's Law that we'll talk about. And basically what that means is that computing processing power doubles roughly every 2 years or so. Now, some people say it's slowed down in the last 10 years, but you can argue about it. And there's a lot of technologies that are in the labs that could reinvigorate Moore's Law very easily. There's photonic computing, there's quantum computing, there's biologically inspired computing. There's all of these things out there that could start a whole new exponential growth. So what people worry about is an AI becoming super intelligent, not just as intelligent as a person, but super intelligent. So if you think about it, it's like if computing processing power increases every 2 years, say, or 3 years, it doubles, right? Well, then maybe we'll have something that's as smart as a human, say by 2030, right? But then by 2033, it's twice as smart as a human. And by 2036, right, it's 4 times as smart as a human. And blah, blah, blah. And you guys, because you're computer scientists, understand exponential growth. And you know that after only 20 doublings, only 10 doublings, that you're looking at something that's 1,000 times smarter. 10 doublings, 1024, right? Basically 1,000. After 20 doublings, you're looking at something that's 1,000,000 times smarter. How long are we going to keep a genie in a bottle that is growing that rapidly in intelligence? Because I can guarantee you, humans, after I'm not 1,000 times smarter than I was when I was your age, you know, much less 1,000,000 times smarter. Maybe I'm a little bit better at some things, but anyway. So what have some people suggested? Well, one thing that's been suggested is maybe we can program our AIs to be good. Okay, so maybe we can program the AIs to be good. And from science fiction, classic science fiction, there's Asimov's 3 laws of robotics. I read these when I was a kid. I loved Asimov. I loved his robot stories. Much better than the movies that have been made. But basically, he proposed that you would have a system of laws coded into the robots, where the first law, the most basic law, is that a robot couldn't injure a human being or through inaction allow a human being to come to harm. It's the most important thing for a robot. The second most important thing for a robot is to do what it's told by a human, except where that would conflict with the first law. So if I told the robot, go and pick up that piece of paper, it would do that. But if I were to tell the robot, go and assassinate Logan McCarthy because I don't like that kid, it would not do that, because my order conflicted with the first law of robotics, which says that the robot can't hurt somebody. Or through inaction allow a human being to come to harm. So if a robot saw that a car was barreling down on a little kid in the street, the robot would be compelled to run to the kid and get it out of the way of the oncoming car, even if it meant the destruction of the robot. The third rule said, well, a robot's got to protect its own existence as long as such protection doesn't conflict with the first and second law. So in other words, yes, if a kid's playing in the street and a car's barreling down on that kid, the robot would run out to save the kid's life, even if it did its own destruction. We would want the robot to do that. However, we wouldn't want the robot to play in the street by itself, right, and get hit by cars and destroyed, because they're valuable pieces of equipment. So the robot has to have the idea of protecting itself from destruction, because it's an expensive piece of equipment, but that can't override a rule given by a human, or protecting a human life. So that was one of the early attempts in science fiction to say, okay, we can control AI. Well, what's the problem with this? Well, the problem is it's just science fiction. It's not real, and nobody knows of any way to build a system that you could put these laws in that couldn't be violated. So it's kind of hopeless to try to program it currently looks kind of hopeless to try to program a system so that it won't hurt us. There's another thought experiment. I have it up here. It's called the Paperclip Maximizer by Nick Bostrom. Basically, the idea there is that even if you had an artificially intelligent system and you gave it something benign to do, say, make paper clips in the most efficient way possible, please. If it became super intelligent, it might decide things like, oh, I need to kill all the humans because they could turn me off. And if they turn me off, I won't be able to make as many paper clips as I need to make. Oh, and by the way, those humans are made of atoms. Those atoms could be rearranged into paper clips. And that would help me maximize my goal of creating as many paper clips as possible. So the idea there, it's supposed to be a silly example, but the idea there is that even a benign instruction could end up being something really, really serious. So I've got 2 minutes left. 2 concepts, the singularity. We're going to come back to this and talk about it. Basically, the idea behind the singularity is that artificial intelligence will be created, and then there's going to be this intelligence explosion, and computing systems will become the dominant intellectual force on the planet, which leaves people worried that we're going to be left behind. And one of the things is we don't want to be killed by them. Maybe they'll take pity on us and make us house cats. That would be kind of scary too. If you want to be really scared, Raymond Kurzweil, look him up, predicts that we'll achieve human level intelligence in a supercomputer in 2029. He's been saying that since the late 1990s, and when he first said it, it seemed stupid and silly. Now it doesn't seem quite so silly when you think about Google and Alexa and gRPT-3 and some of the other things. So we're talking about something that's going to occur in your lifetime in the relatively near future. So, you know, these are interesting questions. What is one of the solutions that's talked about? Well, Elon Musk is working at a company called Neuralink, and the idea there is that we'll be able to somehow merge with computers, and if we can merge with them, maybe we can join in that singularity and the exponentially increasing intelligence, and maybe that'll prevent us from being treated like house cats or being, you know, turned into paper clips. Anyway, that's it for today's lecture. I'm going to kill the recording here, but I'm going to stick around if people have a few questions. I'll be happy to take a few minutes and ask them. Thank you for your attention. Like I said, I'll stick around for a little while, but I'm killing the recording now, so you're free to go live your life. Take care. I'll see you next week. Bye-bye.